Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm very glad to introduce Xavier Angara today. He's a speaker. Xavier and I go back a long way. We worked together in Panasonic for a couple of years, 3 years. And then he moved to UPC, where he studied his PhD. And so he's on a fellowship, 2 fellowships actually, in Berkeley. And he's going to finish it in October and move to LIMSI. So he's going to talk about speaker diarization for meetings. So
thank you, Patrick. Well, see, for the people that don't know me, which are lesser than I thought. So yes, I'm from Spain. UPC is in Barcelona. It's the Technical University of Catalonia, and ICSI is the International Computer Science Institute in Berkeley, which I've had the honor to be there for the last 2 years, and that's where I've helped improve the ICSI diarization system, which I'm going to introduce today with all its different parts. So I understand a couple months ago, maybe a fellow friend of mine came up and talked to you about the system a little bit and about use of delays to improve diarization. I'm going to go through that part a little bit, but then I'm going to talk a lot more about beamforming and special things we do for meetings environments to improve it. So this is a little bit the outline of the talk. Please feel free to interrupt at any point with questions. If not, it's a little boring for me to talk all the time. So the outline is we're going to see what is actually speaker diarization and introduce the speaker evaluation metrics that we're going to see numbers about in the rest of the talk. Then I'm going to talk about the ICSI diarization system for meetings, which I would separate it into 3 main modules: speech, non-speech detection, automatic acoustic beamforming to deal with the multiple microphones that we have in our meeting room, and the diarization module. And then I'm going to talk about the main application of this system up to the date. This is a research system which has been to participate on the NIST rich transcription evaluations. I'm going to talk about the evaluations, about what I think of them, what they are about, and also a little bit about ICSI's participation on them. Finally, conclusions on future work. So let's see what is speaker diarization. So we have a signal, speech signal. This is from a Spanish news program, and although we cannot see much in here. What we do first, we do a speaker segmentation or a speaker change detection, which analyzes the signal and finds the change points between speakers, or if in change detection between any acoustic difference in the signal. Maybe it might be the same speaker with different backgrounds, so it's going to find the change points in these places. Next thing we do is we associate an ID, which is only an ID, it's not the name of the speakers, to each one of these segments, saying, okay, so this speaker over here is the same speaker we have over here, and speaker C here is the same as in here. This is called speaker clustering. Then we might want to add some extra annotations, so metadata, which, for example, could be saying, these are males, some other people are females. We have noise over here. We have telephone speech, studio speech, etc. All kinds of metadata annotation that we can put. And finally, we can use an ASR system to put the actual text that we had. This whole thing, it's very interesting, so we can add a lot of extra annotation to the data. So what is speaker diarization in this whole ensemble? Speaker diarization is considered to be the speaker segmentation plus speaker clustering modules. So that's the system I'm going to talk to you about. I was thinking about the applications that we can have on speaker diarization, and I came up with 3 main blocks. On one side, rich transcription is actually the slide we saw before. It's adding all this kind of metadata annotation to the recording. This metadata can be used for machines to be able to read the information better and do stuff like summarization or speech translation. or even for humans to do some multimodal, some information extraction from the data. Instead of listening to the whole thing, you can do searches on the audio. Another application, main application, has been on STT, on speech-to-text systems, where the segmentation part will help you cut the audio into parts that are homogeneous, not cutting in the middle of the words, so that you can have small, relatively small sentences to analyze. And the speaker clustering part will let you do things like BTLN, stuff like that, where you have homogeneous speech from one speaker or several speakers with the same kind of speech to train your to adapt your models. And then a third main block would be the pre-processing for other systems, where these systems are based on one speaker processing, like speaker recognition, localization, or speaker indexing, where we want to have the actual name of the speaker who spoke, which our speaker diarization system is run before to cut the data into the different speakers, and then we want to post-process. So let's see particular areas of application of speaker diarization that has been researched over these last years. A lot of research was done in the past 3-4 years on the broadcast news environment, where these are recordings from radio or TV of news shows or debates, etc. There was a lot of emphasis on this because of the DARPA years program, and NIST, the National Institute for Standards and Technologies, was doing evaluations yearly to evaluate the different systems from the different teams that were participating on the program. The news have different characteristics in which the audio has commercials and with music and speech on them. We have professional narrators where there is a mixture of unscripted and scripted material in there. And we normally have only one channel of pretty good quality channel, except when it's out in the field talking, which is being able to be processed. So the systems in here are mono-channel, single-channel systems. And then we have the meeting rooms, which it's recordings in a conference or a lecture room. A conference room would be around a table where different people are having a meeting, talking to each other, and a lecture room would be like what I have now with some question and answers from the public. We have an increasing emphasis on this, mainly due to these European projects named CHIL and AMI, and also the Swiss IM2 projects and some independent research from companies, maybe Microsoft. The characteristics is that the non-speech is normally due to silence or eventual noises like dropping a pen or closing a door. Speech is mainly spontaneous, and we all normally have more than one channel to process. So we have to deal with a multi-channel system, see how we do that. And then we have other research areas like telephone conversations, pilot, control tower conversations, etc., that there has been some efforts in the past on that areas, but now I don't see any more papers on this. Let's take a look at in what way normally in the past speaker segmentation and clustering has been done. There is many different systems that have been proposed in the bibliography, but I would collect all of them in something like this schema, where we have an input signal, which needs to be diarized, or segmented and clustered. Over this signal, we do a feature extraction, and we compute a metric of each of the different instances of the signal using maybe acoustic models or just a metric between the data, so some parameters extracted from the data. And then we do a change decision, a speaker change decision, which gives us the change points on the acoustic data. This module is normally used as a first part, the segmentation module, as a first part for a speaker clustering module, which after we have the change points, we're going to maybe use some cluster models, compute some dissimilarity metric between the different segments obtained up here, and determine which segments are from the same speaker or from the same background condition. We're going to keep doing that while we assert a stopping criteria, and then when we say, okay, we have clustered all the speakers that there are, we have the optimum amount of speakers, we're going to output and get the output that we saw before in one of the slides, where we have an ID for each of the segments belonging to the speaker that spoke it. Let's see in a little more detail in speaker segmentation what has been used in the past. So segmentation can appear on its own, as used on STT, as we saw before, or as a previous step for speaker clustering. Sometimes these techniques, though, cannot be separated very much. They are all invisible. They are not divisible, like in the ICSI diarization system, as we will see afterwards. There might be many classifications about the systems that we have for speaker segmentation, but this might be one of them. We have first systems based on silence detection. These are mainly used for ASR systems. There's decoder-guided systems where we have ASR models, phone models, and a silence model, and then whenever the silence model is selected, we have a change of speaker. And we have some different sorts of silence detectors, energy-based or other features-based. Then we have another blocking here, which is systems based on acoustic modeling, which are normally bigger models, broader models, like multi-phone models. That's the difference with the decoder-guided, which we also decode the signal, and in the change points between models, we detect that there is a change of speaker. And then also systems based on metrics. Many different metrics have been proposed, like the generalized log likelihood, BIC, KL, KL2, etc., where we normally have two scrolling windows, and we compute in the middle point this metric between the two windows, and we decide in the maximum points or the minimum points of this metric that there is a change point. What about speaker clustering? Well, as we saw, the aim of speaker clustering is to group together all the segments that belong to the same acoustic source in a recording, which might be a speaker or a background condition. In the systems that has been proposed over the past years, most of them usually don't use any prior information of the speaker ID or the number of speakers we have in the recording. And we normally use for speaker clustering two kinds of metrics. First, a distance metric between the different segments to say how similar these segments or clusters are. And then we keep clustering them, and we need a stopping criteria to stop this process at the optimal amount of speakers. We have two different strategies we can follow. There's a bottom-up clustering strategy where, if we look at this pyramid, if we interpret this as a lot of initial clusters and this as a single initial cluster, bottom-up clustering would go from a lot of initial clusters up to the optimal amount of clusters by merging the different clusters. This is used normally by using the segmentation as an initialization in here. And the top-bottom clustering or top-down clustering goes from only one cluster until the optimal amount of clusters. Let's look at some of the systems in these two areas. Bottom-up clustering is very popular because we can use the speaker segmentation to start with. And it normally, many papers or publications, it uses the Bayesian information criterion, the BIC, as the distance metric between different clusters. This BIC criterion is the likelihood-based criterion penalizing the metric by the complexity of the model. So bigger models are more penalized if they don't fit well the data. And there has been many modifications of the BIC metric proposed in the literature in the past, trying to solve some of the problems that it might have with short amounts of data or disparity in the different models, etc. Also, apart from the BIC, also many other metrics used in segmentation can be also used as a distance between clusters. And just as a note, in recent progress, mostly in broadcast news and recently also adapted to meetings, diarization, it has shown that some speaker ID techniques, map adaptation of UBMs, can give you a lot of gain when doing speaker diarization, mostly because you have very little amount of training data, so you can actually adapt these big models and do a better job in stopping criterion and also in comparing the different models. The other big block of techniques for clustering is the top-down clustering. This hasn't been that much used. There is very few systems that actually use this, but I thought it was worth it to mention a couple of them that I found. The first one is the original system that Cambridge used, and the EHMM system used at LIA in Avignon, France. These two, they start with one cluster, and they keep splitting into different clusters until they get to the optimum amount. They either start with training a model with all the data in the meeting or in the show, in a broadcast news, and then splitting this into pieces, or starting with a subset of the data and then using the other data iteratively to create new clusters. And they normally use a global likelihood criterion to stop this processing. This is a slide you might have seen in the past. I put it here because I'm going to talk from now on about systems and about errors. So before I tell about any error, I wanted to define what the different kinds of errors that I'm going to talk about are. This is a possible segmentation of the data. This is the truth. And this is a segmentation that we give in our hypothesis system. This is a time domain, time scale. So we have two kinds of errors given speech, non-speech detection. The first kind of error is false alarm, where we actually say in our hypothesis that there is some speech and there is not. And we have also some missed speech error, where we say that there is no speech and there is actually speech. Another kind of error we have is the speaker errors. In this case, we have the same kind of figure, but we have to split the truth into the different speakers. Each one of these lines is a different speaker that speaks in different points in the recording. As you can see in these points, we have some overlap, more than one speaker speaking at the same time. So in here, we can differentiate between, with different error regions. The first error region is a mislabeled speech, where we say there is a green speaker here and there is actually a blue speaker here. We have also overlap errors, where we say that there is only a red speaker speaking, and yes, there is a red speaker speaking, but there is also a green speaker here. And we have both of the errors from before combined. There is here first an overlap error, where we missed this speaker over here, and an error of mislabeled speaker. There is some overlap error here, plus all this speaker that was mislabeled as a green. So these kind of scores are used by NIST in their evaluations, and the sum of both missed speech, false alarm speech, and all these kinds of speaker errors is what determines the diarization error rate. Is the total percentage of misassigned speech in the meeting. So we're going to continue.
Can you just go back a slide?
Sure.
So the error in that first, the leftmost one, wouldn't the error bar continue out to cover the false alarm speech there?
This one here.
Or the missed speech?
Yes.
Oh, it's false alarm speech, yeah. So that.
This one here?
Right.
Yes, but in here I just wanted to show the speaker error.
Okay.
Yes, this would be a false alarm speech.
Okay, and you really paid twice in the far right thing where you.
Yeah, you get twice the hit.
But it was blue and red also.
Yeah.
You pay twice for that.
Yeah. So you can have more than 100% error in your systems, which is pretty funny when you get that, yeah. So let's look at the ICSI meeting diarization system.
So the time, so you divide by the total time of the meeting, right?
You divide by the total time.
The best single hypothesis can have some error. Right? Is divided by the total time, not the added speaker time.
Yes, just the total time is one time. So there will be for these overlaps there will be only one time. You divide by that. But if you make a double or 3 times the error, that adds up. That's why you get.
Are you able to hypothesize multiple speakers? So can you say like, oh, it's red and green and blue?
You should be able to. You should be able to detect when there is overlap and to say which speakers are there. In the current system, it's not.
But what about the scoring? In this case, is it possible to produce an output that will be scored as correct?
What do you mean with that? If the hypothesis can create an output that has the 3 speakers on it.
Right. Are you allowed to produce hypotheses of that form? Will the scoring program score hypotheses of that form?
Yeah. If you say, okay, for this segment over here, I have speaker 1 and 2 and 3. Yes, I mean it scores. But the current system.
It's actually possible to get
it 100% correct.
Right.
Yeah, it's
0% error.
exactly, yeah, it's possible, of course, yeah. But what I'm saying is, none of the systems nowadays are able to not even say which speaker is here, but to detect overlap. I mean, there is this year in the NIST evaluations, overlap speech was the main metric. So I'm going to talk about this a little later. You can either ignore these regions, say, okay, this doesn't exist, I don't score in here, or actually score, count these 3 times. And this year, counting these 3 times was the main metric. And many people tried doing things to detect it, but nothing works yet. So that's an open question still.
So what is the input in this case? Just a mono wave file?
No. In the meetings, you have 20, 30 channels, whatever number of channels you have in the meeting. So you have to deal with that. That's actually what I'm going to talk in the system. It's the second is acoustic beamforming module. So let me go on and you'll see a little more in this. So the ICSI meeting diarization system, it's composed of this speech non-speech module to detect when there is speech and non-speech in the audio, an acoustic beamforming module that deals with multiple microphones and ends up with only a single microphone that is then analyzed by the Diarization module. So this is the full processing. So answering to your question, we have multiple microphones, as many as you want in the room. We do some SNR enhancement with winner filtering. And then we use a delay sum modified processing to fuse all of these systems into a single channel, which is supposedly of better quality of any of the single channels before. And then the single channel is fed into this single channel diarization system, which we also get the speech non-speech to work on this signal. And then you can see 2 different arrows here. One of the arrows is the acoustics. The other arrow is the extra information that we can obtain by processing the different channels with the delay sum. So let's see at the 3 different modules of this. First, at the speech non-speech module. Little introduction is the speaker diarization.
Another question. Did you ever try just like decoding each channel separately and then rovering them?
I didn't try it. The people in Avignon, they tried it in RTO4S in 2004. I don't know if they actually did rover to merge them, but they did some sort of thing with the scores at the end, and it didn't work at all. Apart from being n times slower than doing this. Yeah.
So when you say multiple channels, what is this? Are microphones like this placed on the ceiling, or this is what we call microphone array, which means microphones?
There is everything.
Just throw away several 5
Yeah.
or 10 microphones in somewhere in the corner.
You'll see it further on. I'll talk about it. So we know we experimented in 2004. Sorry.
What was the earlier question? I didn't catch the earlier question.
Which one?
The first one.
The first one is how do we, if it's possible to get the multiple channels processed independently with the single channel diarization, and then doing the merge of the results at the end. And I said, it's been tried, not by me, but by other people. It didn't really give good results. They actually switched to a schema like this after they tried that.
Are the clocks all synced?
Supposedly, hopefully, yes. There is a case where they are not. But I'll make a comment on that. The ICSI meeting recordings, they were not synced. But supposedly you have the right hardware. So going back, speech non-speech detection. We saw that by adding a speech non-speech model to our diarization, it improves results. The thing is, we have very little data to train our initial models. If we throw non-speech in there, we diminish the possible discrimination between the different speakers. So we better get rid of the non-speech beforehand and try to process only the speech parts to be able to see if 2 different clusters are from the same speaker or not. For broadcast news, we've been doing it using a 3-state HMM system trained on a lot of broadcast news data for speech, non-speech, and other events. But for meetings, even though we tried the first, in 2005, we tried using this trained model-based system. We didn't like the fact that we had to train the data. And the fact also that most of the non-speech that we want to get rid of is based on silence. Made us develop a new hybrid system that tries to detect this silence and actually does a better job than this initial model-based system in not really detecting the speech-non-speech regions. The speech-non-speech error is more or less the same, but it tunes very much better into the diarization afterwards. So this is the hybrid system that we developed for meetings. And I call it hybrid because it's basically a back-to-back system. We have an energy-based detector and we have a model-based decoder. The energy-based detector, it's typical, we calculate the energy of the signal, we do some signal processing modifications, like we do the derivative of the signal to improve the change points, a couple of things. And then via setting a threshold, we detect what is speech and what is non-speech.
What is signal and what is pulse, actually?
What is what?
When you have pulse silence and when you have non-pulsed signals.
Exactly, yeah, exactly. So, so in this case, the difference in this system is that we don't want to set this threshold. We don't want to set this threshold to the exact data. So we start setting this threshold very, very low. So we say, okay, almost everything is speech. There is no non-speech. And then we assert this silence assertment here, which actually says, okay, how much non-speech we detected. If we detected very little, we go back and we adjust the threshold. We higher the threshold a little bit, and we rerun the system. And we keep doing that until we have enough non-speech data in here. This enough non-speech data condition is just having long enough segments of non-speech in order to be able to train this model-based decoder. And this was tuned so that the missed speech rate in here was very, very low. We want to have very pure non-speech models over here, and we don't care about the speech models. They can have non-speech in there. Once we have this output, we go into this model-based decoder, which is actually basically two models, one for speech, one for non-speech, which we initialize with the output of this system. And in here, we just do some iterative segmentation and training of the data in order to get an output when the overall likelihood converges. And that's the output we use for the diarization. I see some potential problems. No?
It's
Yeah?
pretty logical approach.
Why not just run a decoder on the original signal that's been trained with some silence in it,
Mm-hmm.
and then it'll tell you what's speech and what's silent?
Yeah, you could try that. I don't know if it would work better or worse, but it's kind of killing a fly with a cannon. It's like a big decoder to do such a small thing.
But you're about to shoot your cannon anyway.
Well, this is pretty fast. This is a very fast system. Like, this is done pretty fast. It's like 0.1 times real time and stuff like that.
The VMC system does boost processing based on STT, and they get some improvement on the test.
Right. Well. Yeah. In this diarization system, we try to keep it as small as possible. So we actually didn't want to put any ASR into it. Although always ASR could help because it gives you the actual words and stuff. Some numbers. For these numbers, we used the evaluation risk transcription of 4 and risk transcription of 5. And there's lots of numbers here. The main things I want you to focus on is if we don't use any speech non-speech system, we have an 11% of non-speech and a 13% of non-speech. But then the final error rate is huge. This is the diarization error rate. The speakers are not well detected. If we use the pre-trained models that I said we use for broadcast news and initially for meetings, we get about a little better here the non-speech of the hybrid system at the output, and little worse in here. But you can see that the pre-trained models, when we use them in diarization, they get much worse results than using the hybrid system. Even though the hybrid system in here, it performs more or less the same as the pre-trained models, the final diarization is more in tune with the diarization module. So that was a great surprise of using this system. Let's go to acoustic beamforming. Oh, wow. So we have many different microphones in the room. So let's assume at first we have a linear microphone array. And we have this formula for an output of a filter and some formula where each of the microphone arrays is delayed a certain amount and is weighted by a weighting function. And then we get the optimized output signal. This time is depending on the angle of arrival of the speech and could be determined by this formula, although as we don't know the angle of arrival of the speaker, we have to approximate it by ways I'm going to talk about afterwards. So couple comments. Well, we'll go to the next one. So what happens in the real case? Well, we don't have a nice linear array. We have microphones here, microphones down there, microphones in the table, everywhere. So we kind of decided to stretch this basic theory and say, okay, we're going to treat everything like a big microphone array and see how it does. And in particular, we don't know the microphones. We don't know how many they are. So we need a technique that can scale. And that for sure we know that the quality and the impulse response of each of the microphones might be different to each other. This microphone here is different than the one I'm wearing now and the one in the table. So we need to account for different quality of microphones and the way that they influence the total amount of the output signal. What's our aim here is to collapse all the channels into one, so we don't have to do a parallel processing of diarization. We just do one. And we want to have an SNR output quality better than any of the individual channels. If by doing all this processing we end up with a worse signal than our best microphone, we better don't do anything. We just detect which one is the best microphone and go with that one. This is a hint of standard delay sum or filter sum technique. We have the different microphones. We have a reference channel. We approximate the time delay of arrival, which is this tau value that we use over here. We compute it with a formula function called GCC-FAT, the generalized cross-correlation phase transform. And in our system, we do an n-best filtering to obtain the optimum delay. I'm going to talk about this later. Once we have the delay for each of the channels, we just delay the different channels, sum them up, and with some triangular windowing, we obtain the sum and the enhanced signal. In our system, we use 500 millisecond analysis window of each of the points, and we slide it 250 milliseconds every way. So we analyze what delay the person is talking from every 250 milliseconds.
Do you work in the frequency domain?
The GCC-FAT works in the frequency domain to obtain the estimate of the time of arrival, but this is all.
So regular DFT.
No, it's a DFT normalized. It's a cross correlation normalized, but I'll show you afterwards. So this is the full processing system, which we could separate into 3 main blocks. Of course, we have a winner filtering at the beginning to improve the signal of the individual channels. We have a part that extracts information from the meeting. Then we have post-processing, which I'm going to talk about, which gets all this information and selects which delays we're going to use for the delay and sum. And then we compute the output signal generation. We're going to go through all these modules a little bit in detail. Answering to your question, the TDOA, the time delay of arrival using the GCC-FAT formula. This is the GCC-FAT. It's basically a cross correlation in frequency domain normalized by the modulus of these values. This actually normalizes the modulus and makes the information of the delay be conveyed only by the phase of the signal. And in normal systems, in regular systems, you do this, go back to the time domain and find the maximum of the curve, and that's your time delay of arrival. But we found that this maximum sometimes was confused by either short impulsive noises. Imagine somebody's talking and somebody else drops a pen or something. Your beamforming will go to the pen dropping for a second and then go back to somebody else. So you don't want that. You want your system to keep focusing on the speaker that's speaking most of the time. Also, we can have systems that when we have multiple speakers speaking, sometimes one speaker will have better energy than the other. So the steering might go from one speaker to the other, from one time to the other. So we decided we needed to do some post-processing to select exactly which one we want. And for that, we have to compute, instead of the maximum of this cross-correlation curve, we compute the M local maxima, and then we select which one we use as the delay. On the information extraction module, we do a lot of things. We compute a global output weighting to weight the output signal so that it has a dynamic range. It's optimized with the output file, just engineering things. Here is about the ICSI meetings. The ICSI meetings were not synchronous. There was a problem in the hardware that made each microphone start recording a little after the other one. The problem is we don't know which microphone is which, so we need to approximate it. So in order for the computation to be better and not to have to use a huge analysis window to compute the cross-correlation, we do a first skew approximation to put all the signals as synchronous as possible. We compute a reference channel. We saw that we need to compute the cross-correlation between the reference channel and all the other channels. We were given NIST gives us a reference channel, which is what they call the most centrally located channel. We didn't trust them. We thought, okay, there might be another channel that is better in terms of cross-correlation with all his neighbors. We compute that using in this step. And as I said before, we do a TDOA estimation of the M-best maximums of the signal. In our system, we use the 4-best. So we do the post-processing. What's that? Well, our first post-processing step is a noise thresholding. It's very simple noise thresholding. If we don't go over a certain minimum value for the cross-correlation, we just filter it out and use a previous value that was okay. So we have a steady signal. We don't have spikes of delays here and there. And the second part is where we select from those 4 best delays, we select which one we're going to use in our system. This is comprised of a 2-step Viterbi decoding. In the first step, we use individual channels and we do a Viterbi decoding of each of the individual channels. We obtain from the 4 best or the M best at the input, we obtain the 2 best at the output. And then we do a multiple channel Viterbi decoding where we select for the 2 bests of each of the inputs, the 1 best used for the delay and sum. Let's look at it in a more detail. The first step, the individual channel, we use a Viterbi. The function, the transition probability from one possible, so in here we have like the trellis where we have the N best, different channels, different maximums of the cross correlation. This would be time. So what we want to see is, this is the channel from signal 1, channel from speaker 1, channel from speaker 2, channel from speaker 1 and speaker 2 are down here. They are not the maximum. They went down here because we maybe dropped a pen over here. And then speaker 1 and speaker 2 are back here again. So what we want to find is the best path according to some metrics that determines, even though our 1 best is here, we can filter this out and select another value that is much better in tune with the values that we have around it. To do that, we use this transition probability, which is a function of the distance between the delays, and the probability of each of the elements, each of the hidden elements, is basically the GCC FAT value we computed before, the cross correlation between the 2 signals. So doing this first decoding in one individual channel, we're going to find the 2 best paths, which in this example, for example, we get that the first best path says, so speaker 1 here, speaker 2, speaker 1, and speaker 1. Second best path, speaker 2, speaker 1, speaker 2, speaker 2. This is an area where we had 2 speakers overlapping plus some pen dropping or some other noises. But we want to have, if we have 2 speakers overlapping, we want to have our system focusing on one of the 2 speakers. We don't care about the other one. We just want to maximize at least one of the speakers in the recording. So we achieve that in the second step, where the second path takes into account the 2 best values of the cross correlation for each of the microphones. And the trellis then is all the possible combinations of the two bests. First best, and second best, first, second, first, etc. And by a similar way, similar transition probability and probability of the signal, we obtain the best path over all these trellis, which in this case, hopefully we'll have, this would be an error, this should be up here. We will have, no, sorry, yes, this is okay. We will have the same speaker selected all the time. So we will have a final TDOA focusing on one individual speaker. Output signal generation, this deals with the weight that we give to each of the channels. As we said, different channels have different noise conditions, different, we don't want to weight this channel the same way as we weight the channel down there, for example. So we did an adaptive weighting function depending on the cross correlation of the channels, how good the quality is of the channels with reference to each other. And this weighting function is adapted pretty slowly, 0.95 adaptation, pretty slowly over the meeting, but it keeps adapting to the different channels. Because, for example, if you have a meeting table and we have two microphones, one over here and one over there, when the person that is next to this microphone is speaking, that one there should be lowered, the weight. But then maybe the other person starts speaking over here, so now that microphone should be lowered and this microphone should be higher. That's why we do an adaptive function.
So there is one number per channel.
One number, yeah, one weight per channel, yeah. That's in that sum that gets you the output signal. Just a comment here, some of the channels are bad, so we don't want them. But we don't cancel the whole channel all the way. We just use the same function as here, the cross-correlation, function of the cross-correlation of the different channels to detect which channel is very bad, and we just don't use it in the output of that particular time. And we sum all the channels using a triangular windowing so that we have some overlap between the current time and the previous times, so that if we actually, for whatever reason, we didn't get the right time delay or something, we still get a pretty smooth signal at the output. So let's go to the diarization module. Diarization is a single channel diarization system because we have now this beamform signal that we feed into it, and it's based on the ICSI's RTO4F system. It's a hierarchical agglomerative bottom-up clustering, which means we get a lot of initial clusters and we merge them until we get to the optimal amount. And we call our system robust because we don't use any training data. We eliminated all training data by changing our speech-non-speech detection. And so, we are very proud to say, it's robust speaker diarization. We still have to tune a lot of parameters. But, well, that's in the works to create parameters that are more robust also to tuning. And this is a whole diarization system. I'm going to say a little bit about everything, but given the time constraints, not much. First of all, we have two possible input streams of feature streams. They are independent feature streams. In one side, the acoustics, MFCCs, 19, no deltas, no zero, no energy, computed every 10 milliseconds. And the delays, we're using the delays from the TDOA estimation, those optimized delays. We use them as a feature to the diarization because this feature is independent to the acoustics. This feature is telling us where we are steering, so the position of the person instead of the acoustics of the person. And they can also help us for diarization. This would be our ergodic HMM system. Each of these rounds is one speaker in the system, and we model each speaker with a set of states, all using the same GMM system. These states are set this way so that we have a minimum duration of one speaker when we do a Viterbi. We set a minimum duration in the meetings for 3 seconds. We still at least want to have one same speaker for 3 seconds. But we set the alpha and the betas down here to be 1 and 1 so that we don't have any constraints by definition on the maximum length of our decoding. How do we initialize the system? Well, initially in the broadcast news system, we had to set a number of initial clusters. and that was set to 40 clusters. And then from 40, you keep merging until you get to the optimum amount. We decided that we better determine the amount of initial clusters by the amount of data we have able to train, because we want to train our models, our cluster models, with enough data. And using this simple formula with total amount of frames, initial number of Gaussians per cluster, and this cluster complexity ratio parameter, which you have to optimize, it gave us a better estimation than just saying, okay, we decide we have 20 or 30 or 10 initial clusters for our system. There's some numbers here. Improvements are not very big, but it indeed helped in other tests. Now we have that our system wants to initialize with 20 clusters, let's say, or 10 clusters. How do we select which data we put in these 10 initial clusters? A system that I called friends and enemies system, which is in some flavor very similar to LBG clustering, is used in order to select these initial clusters into clusters that have homogeneous data in it. First of all, we do a speaker change detection. Then we start selecting one cluster of the one segment of the segments we found with the change detection, and this segment selects his friends. Like in here, we selected this segment. He selects his friend in green. And then these two segments together, they select their enemy, which is the first red one. This red one selects his friend. And then finally, when all the friends and enemies are selected, we get to the number of clusters we want to have. We do a segmentation, and we put together all the rest of the segments to their closest cluster. In order to compare to select friends and enemies, we use a cross-correlation between the different segments. Cross-correlation likelihood metric, yeah. Agglomerative clustering. Well, we initially have our system doing several iterations of Viterbi segmentation and models retraining so that our system starts kind of converges. We found that it's better to let the system converge to a steady state before starting the clustering. And then we start the clustering by comparing the different clusters together in cluster pairs using the big metric. But in our system, the big metric by itself is a likelihood-based metric. As I said before, it's penalized by the complexity of the models. This is the formula for the comparison of this big model, which is composed of clusters I and J, and compared to the individual models I and J. And we're going to say if either a model together or the two individual models is better. This penalty term is composed of a lambda parameter that needs to be tuned. The difference between the number of parameters between these two guys and this model over here, and the logarithm of the number of frames in total in the system. This person, Jitendra Mehra, proposed in his thesis work, and he was the first implementer of the ICSI system, that if we constrain the delta big to have this model with the same total amount of parameters as the sum of these two, this parameter can get eliminated. It goes to 0. So we use this, and this is like a GLR metric, generalized log likelihood metric, where we constrain the number of parameters between these two different models here. We compute the delta big of all the cluster pairs, and we will merge the cluster pair that has the biggest delta big, which says it's the closest clusters, most probably coming from the same speaker. And given that we take out all this threshold over here, or this penalty term, we have a threshold for the big that any cluster pair that has a delta big bigger than 0 means that it's the same speaker. Any cluster pair that has a delta big lower than 0 is different speaker. So we can have a stopping criterion based on big when we stop when all cluster pairs are lower than 0. When we do these comparisons with big, we find a problem. Is that even though we have our speech non-speech detector system, that speech non-speech detector has a minimum duration to detect non-speech in order for it not to have many false alarms or many misses. So that means that our clusters will still have some non-speech added to the cluster data. So this non-speech added to the cluster data, in some cases, it still is prejudicial to our system, making our delta V comparison be lower than 0, and therefore not clustering, not merging two clusters that would be from the same speaker, and getting us an output that has a lot of error because this speaker that should be speaker 1 has been considered speaker 2. This can be seen in these couple plots in where, for example, here I did a test where I knew what was speech and what was non-speech in a whole recording, and I created a model of speech and non-speech. I computed the likelihood of the speech and non-speech, and I plotted knowing what's non-speech and knowing what is speech. This is the likelihood plot. No, sorry, this is a histogram, and so we can see that the likelihood, will be the likelihood axis. The likelihood is higher always for the non-speech regions, given the same model. So given that, we can create a simple averaged likelihood function that we can evaluate on our data and be able to filter out all those frames that we consider that are non-speech in our cluster before we compare the two clusters. Doing this frame-based clustering, we have to select how much of the data we filter out according to this likelihood metric. We found a minimum at 80% of the data. We throw the 20% of the data with the highest averaged likelihood given our models, we can get the best results, which drop pretty consistently from our baseline not doing any purification to our one. This is two different metrics depending on how we do the averaging that we get the optimum amount for the second metric here. So this is the part that was presented a couple months ago by Jose Manuel Pardo when he came up, which I'm going to go through very fast. So we can see that we have a gain by using the time delay of arrivals from the delay sum module into our diarization module. So we found a way to put together the MFCCs and the TDOAs by having two independent streams in our system, modeling them two independently, and then getting our total log likelihood of the data as a weighted sum of the log likelihoods of the acoustic streams given the acoustic models and the delay streams given the delay models. This translates also in the delta big, that the total delta big we use in our system to compare two clusters is the weighted sum of the two different delta bigs according to the acoustics and to the delays. We show here that you have to define this alpha parameter here, which has to be hand-tuned according to some development data, and we saw that for about 0.9 alpha, giving 0.9 weight to the acoustics and 0.1 weight to the delays, we get the optimum results. We can see that only using delays gives this result over here. We get a nice gain. This was on RTO5 data set. Nice gain by using a little bit of the delays in the system. Let's talk about the NIST risk transcription evaluations real fast. So, as I was introducing before, NIST has sponsored many risk transcription evaluations. They normally used hand-transcribed development data provided to the systems, to the sites, so they can develop their systems. And then they do the evaluations, they send the results, and then we do a workshop at the end where the last 2 years coincided with the MLMI workshop where we share the results from the different labs. ICSI participated on RTO3 and RTO4F in the broadcast news evaluation, and since I arrived at ICSI, I participated also on the RTO4F, and then I've been participating on RTO5 and RTO6 in the meetings domain. In my opinion, there is nice points and bad points of doing these RT evaluations. The bad points is that you really need a lot of manpower. I've been full-time developing the ICSI system and participating on the evaluations for the last 2 years. You have to do a lot of data processing, a lot of changes to be done in the system to adapt to each year. And it's, in my opinion, a little too far from actual systems. In an actual system, you normally have how many people are in the room. So you can put that in the system. In here, you just have to find that out. But it has some very good points. It's a perfect situation to compare your new techniques with other people's new techniques because you're using the same framework, the same databases. It's a very good way to get in touch with people working on the same area. And it's a wonderful opportunity, like in my case, for core research for a PhD thesis presentation, for example. Some evaluation characteristics. We have to answer to the question, who spoke when? This is the diarization question. We don't have any information on the amount of speakers or their identities in the data. We have information about where the meeting is held. And each of one of these meetings has different acoustics and microphone settings. Some of them are known, but we don't use them in our systems. Speakers might move or not in the meeting, and up to 5 speakers are allowed to be overlapping with each other and are labeled as overlapping. There is many conditions that are evaluated on the system. Single distant microphone, only one microphone in the room is provided for our systems to run on. Multiple distant microphones are microphones in the middle of a table of a meeting room. People are around it. Then we have some microphone arrays. This is the NIST Mark III array, which is a 64 microphone array, linear array from NIST. And T arrays, these are from Chill, which is 4 microphones in the T put around the room, normally for speaker localization, but you can do also some beamforming and use it for diarization. There is a condition called ADM, which is the sum of all possible microphones in the room. Everything gets into the system. And the individual headphone microphones which people are wearing, some of the people are wearing in the room, which we don't do diarization on them, but they are used for transcription and all the other stuff. And as I hinted before, we have non-overlap condition for scoring and overlap condition. Non-overlap just ignores the overlap regions. It doesn't score on them. And overlap has been the main metric this year, which scores on the overlap regions. Just a comment on hand alignments versus forced alignments. NIST has been providing hand alignments for meetings evaluations where some people listen to the individual headphone microphones and they transcribe where each person speaks in the meeting. And forced alignments are created using the headphone microphones data plus the transcription of what was said and using an ASR system and getting the times of each of the words, and then you can collapse it and get a segmentation, a forced aligned segmentation. Hand alignments have some problems. We have labeling inconsistency. Different labelers, different people have different methods for labeling the data. You have sometimes in the individual headphone microphones, you hear things that you cannot hear in the table microphones because they are too far. You have too much noise. And they are very expensive to produce. You have to create some manpower there to label it and label it well. For this reason, we generated our forced alignments using our ICSI ASR system, and we used them in our development set for RTO6. What did it entail? Well, these are official results for RTO6. I'm not allowed to say who won, but you can see in here. The blue line is the human-created labels, which were used in the actual evaluation. And then NIST created 2 forced alignments data with the LIMSI forced alignment, the LIMSI ASR system, and our ICSI system. And they ran also the system outputs in this forced alignment data. You can see that the results are very parallel to each other, and they differ a lot from the other results. And you can see our system, how we were tuning to the forced alignment, so we got a huge hit by being evaluated on hand alignments. But still, our results are pretty good.
So what's the granularity on the resolution of the errors? Milliseconds? Or?
Yes.
So sound travels about a foot per millisecond, right? So if you have microphones that are separated by 12 feet, you could be off by 12 seconds just from a distance from one microphone to another microphone. Where's the relative location, right? So is it just assuming somebody's sitting in the middle, or
In 12 milliseconds.
not 12 seconds, right? 12 milliseconds, yeah.
And they have a 500 milliseconds frame.
No, there's a color, right, in the scoring.
This was what?
It's
0.3 seconds color in the scoring.
What is it?
Yeah,
There's a color
yeah.
interval there. There's a free bonus.
But the references are created according to this reference microphone, central microphone, and so in any case you have this color that allows you for some error. So it in terms of the scoring, it doesn't really matter which microphone you would use to create the references. A human transcriber wouldn't be able to find these exact points. On terms of the signal that inputs to the system, it does make sense to align them. Because, like for example, one of the systems this year, they didn't do any time delay estimation. They just summed all the systems, and the output signal is much worse with a lot of echo compared to the time aligned signal. Participation on the NIST evaluations. In here, I just wanted to show a couple tables. In here, there were 4 meetings evaluations in the past that used meetings as their input. And I used a system, this year's RTO6 system, and I evaluated all these data sets. You can see the hand alignment references gives us, in overlap, for example, a 43% on the single microphone case, 36 on the multiple microphone case. We get a pretty big gain by using a delay sum, using beamforming at the beginning. But if you look at the numbers more carefully between overlap and non-overlap columns, which this uses all the overlap, everything is in there, this ignores the overlap, there is pretty big differences between one set and the other of from 6 to 15% difference by using overlap or not. That made me suspicious that people that created the transcripts for this one over here were not the same people, or changed their way of creating the transcripts in RTO6. It's 4 years, people change. So we did the same test using the forced alignments. Now this difference goes from 6 to 15% to 2 to 5%. So I believe this is much more consistent. Also results, you can see they lower pretty much. We go from a 36%, 43% to 27, 21%. And so I believe this is more representative of the current system performance.
So if you look at the places where the human and the forced alignment differ, who's right?
Well, so I looked at the signals themselves with the references. One thing I noticed is that many overlap regions were labeled pretty clumsily. If the overlap is actually a or something like that and takes less than a second, they would label maybe 3 seconds around it. So, when you evaluate your system on that, your system at most will tell you, okay, this is the overlap 1 second or half a second, but all this extra time is error that you're not expected, but you're scored for. And apart from that, the exact places of changes between speakers, they are more or less the same. They are pretty consistent. And another thing is the difference in the non-overlap score. We can see between for example, 31 and a 23. This is due to the non-speech. In the forced alignment system, you put the rule, okay, any non-speech region bigger than 0.3 seconds, that's the rule that NIST puts, has to be labeled as non-speech. And the system should be able to detect it. The system also tries detecting that. But in the hand alignments, the labelers, how does a labeler here, okay, that's bigger than 0.3 seconds, this is a non-speech. They pass, they don't see many of those. So that's also accumulated error that your system tries doing better and the real labelers don't see it. Finally, and sorry I'm going a little over time, I have presented today the ICSI system for speaker diarization of meetings. We have a robust pre-processing module which takes advantage of these many microphones you can have in the meeting, trying to improve the quality of the signal that you're going to diarize. The diarization system uses agglomerative clustering on acoustic and location-oriented, location-based data. It's totally train-free. I would say it's robust. You might not agree, but it's more or less robust to the changes in the data set. And there is lots of things to do still. We have to address a thing called show flakiness, which means you have a show, you have a meeting that does very well, 2% error rate. And then you have another meeting that goes to 50% error rate. Why is that? Why is our system performing? Not only ours, all the systems nowadays perform like that. Why isn't it consistent? That's called show flakiness. There's some explanations still not defined, not solved. The system is pretty slow. We want to make it a little faster. And also, I would like, in the future, if I can work on the system more, to orient it to a real application, see how it can be helpful for real products. And regarding the beamforming signal, this is my ICSI website, and I'm kind of cleaning up the code. I'm going to release the beamforming as an open source code for research, so you're welcome to take a look at it and comment it and turn it in whatever you want. And this is most of the things I've talked about today. There is a paper on this I published over these 2 years. You can possibly take a look at these slides afterwards and get these papers. And that's all.
Thank you.